Okay, now let us go for the last video of this lecture, and it is about integrability of continuous functions. Okay, and this is the last section. Okay, theorem says the function f from AB to R is continuous. And then f is integrable on AB. Okay, and so notice that the only hypothesis we made at the beginning was the boundedness of the function. And remember that if a function is continuous on a closed and bounded interval, then it has maximum and minimum, so it is bounded. And I give you the proof, and again, let epsilon larger than 0 be an arbitrary positive number. P is a partition of AB to be specified later. Now you know also the strategy in some proof. We say something needs to be specified later. And here we consider the upper sum of f with respect to this partition minus the lower sum. And this is sum for I equal to 1, or like in the previous video, let me use the letter j from 1 to n of capital Mj minus small mj delta xj. And of course, capital Mj is the supremum of f for x in xj minus 1 xj. F is continuous, the interval is closed and bounded, so by Weierstrass theorem there are maximum and minimum. So this is the maximum of f. Xj minus 1 xj. And this will be f of x bar of I, where x bar j, where x bar j is the point that corresponds to the maximum. Of f in the interval xj minus 1 xj. This is what we will call a maximum point. There will be a difference between maximum, which is the maximum value of the function, and maximum point, which is the point where the function takes its maximum. Okay? So, because by Weierstrass, as we know very well, there exists x bar j in the interval xj minus 1 xj such that f of x bar j is equal to capital Mj. In a completely analogous way, small mj is equal to the infimum of f of x for x in xj minus 1 xj. Again, by Weierstrass, this is the minimum of f for x in the same interval, xj minus 1 xj. This is equal to f x tilde j, where x tilde, where the existence of this x tilde is guaranteed again by Weierstrass theorem. So Weierstrass says that there exists an x tilde j in xj minus 1 xj such that f of xj is equal to x tilde j is equal to mj. So now let us go back to this key quantity, so the difference between capital S and small s. So we have capital S fp minus small s fp is equal to j from 1 to n of f of x bar j, so the maximum, minus f of x tilde j, the minimum, and here xj minus 1 delta xj. Now be careful. I say the following, that f continuous implies the following, that there exists delta larger than 0 such that for every couple of points x, y in the whole interval AB, and the distance between x and y less than delta, we have at the end f of x minus f of y less than epsilon divided by b minus a. This is not immediate. We will go back to this. This is not the definition of continuity. Okay? This is highly non-trivial. So we will discuss this after the proof. Now choose P in such a way that the maximum for j between 1 and n of the size, the size of the interval, which is the delta xj. So namely the maximum of the sizes of the interval of the partition. So xj minus 1 is less than delta. Therefore, at every interval of the partition, the distance between the maximum point and the minimum point inside this particular interval, of course, cannot exceed the size of the interval in which they lie. So it is less than delta, since x bar j and x tilde j are in this interval xj minus 1 xj. So f of x bar j minus f of x tilde j will be less than epsilon divided b minus a. So let us go back here. When we want to estimate the difference between the upper and the lower sum with respect to the partition P, we have capital S Fp minus small s Fp is less than sum j from 1 to n of the distance between the maximum and the minimum, which is less than epsilon divided b minus a, xj minus 1. And this is equal to, collect out epsilon divided b minus a, sum for j from 1 to n, xj minus 1. This is equal to epsilon divided b minus a, and as usual, so you have x1 minus x0 plus x2 minus x1. It is the usual telescopic sum plus xn minus 1, and you know how it ends. Everything cancels except xn, which is b, and x0, which is a, so this is epsilon. So we have that there is a partition. So given an epsilon larger than 0, it is possible to find a partition such that the distance between the upper sum related to this partition and the lower sum is less than epsilon. This is the end, by the lemma proved in the last video. We have that f is integrable. And this is the end of the proof. If you want to clarify a bit what happens in this proof, consider a picture like this. You have here an interval AB and then a continuous function, something like that. Then you introduce a partition, and consider, for instance, this interval here of the partition. In this partition you have, horrible. Okay, but we can easily recover. Inside this partition you have no, this is not the minimum. The minimum is here. You have the minimum mj and the maximum, which is here, capital Mj. So here you have x tilde j, and here you have x bar j. And you see that you want to choose the intervals of the partition in such a way that every interval is less than delta. So for instance, delta can be this guy here, for instance. Every interval here is smaller than delta. Then, of course, you have that the distance between the minimum and the maximum points is less than delta, and then you can do whatever. You can do the estimate. The estimate which is allowed by this strange statement that now I need to discuss a bit. So I copy it, and I want this to be here, and so now let us discuss the following statement very quickly. One could really spend some hours on this, but this is not the scope, in the scope of our course. The following statement. So the first point, that this is not the definition of continuity. This is something more. Why, for instance, consider the following example. F from 0 to plus infinity to r that associates to every x its squared, so the parabola in the positive half line, just to fix the idea. So this is the parabola. And then I want to convince you, my thesis, so what I want to state, I will not give really a proof, a formal proof of some, but it is not true. So even though f is continuous, it is not true that the statement we copied before, this statement here, it is not true that there exists delta larger than 0 such that blah blah blah. This is false. Why? Start from the last statement here. So indeed, if you have f of x minus f of y, so let us consider just epsilon, not epsilon over b minus a. F of x minus f of y is equal to x squared minus y squared, which is x minus y times, all is in absolute value, x plus y. Okay? Now let us suppose that x minus y is less than delta for an arbitrary delta, so even very, very small. Then we know that x squared minus y squared is less than delta times x plus y. But x plus y, this is the key point, x plus y can grow arbitrarily large. This is the main point. So, whatever delta and epsilon are, we will have that delta x plus y will exceed epsilon, provided that x and y are large enough. Okay, this is very, very easy. So this is I can go to the picture here, and the idea is that The idea is that here you have what is the underlying idea. Okay, let me copy here. The underlying idea in the definition of continuity at a point, in the definition of continuity at a point, x bar, which means that for every epsilon larger than 0, there exists delta larger than 0, such that if x bar minus x is less than delta and x in the domain of the function, then f of x minus f of x bar less than epsilon. In the definition, delta, the value delta, can depend both on epsilon, and this was already stressed when talking about sequences, but also on x bar. This we saw it when we concluded for the continuity of x squared. Remember, there was this x squared plus 1. But I don't want to repeat that proof. Consider an x bar here, and then an epsilon. This is f of x bar. You can consider an epsilon like that. In order to remain into this stripe, this is the delta. Okay? Now consider another x bar, for instance here, purple x bar. This is x bar. And this is f of x bar. So let me call it x bar 1, for instance. F of x bar 1. And here, consider the same stripe with epsilon. So here is the first, here is the second, and see what is delta now. Sorry. No. Notice that here, with the same epsilon, so this is a with 2 epsilon, this is with 2 epsilon. So with the same epsilon, the delta we can take here is much smaller than here. So delta depends only on x bar. And the main point is that it is not possible to take a delta larger than 0 that works for every x bar. At fixed epsilon. Delta tends to 0 as x bar tends to plus infinity, which means the farther you go along the x-axis, the smaller becomes your nice interval. Okay? But here, what we are asking in the proof is exactly that there is a delta that holds for every x minus x bar, such that when x minus y are closer than delta, then their images are closer than epsilon. So here, in this statement, we are asking exactly that there is a delta which is good for all points. Okay, in the proof, we asked for the existence of a delta which is good every point. This is what is called uniform continuity. There is a delta that is good for everybody. But in the hypothesis of the theorem, we just asked f to be continuous, not uniformly continuous. So did I cheat? Did mathematicians cheat when they say that continuous functions, all continuous functions in a finite interval integral? Of course not. And why? What is the solution here? The solution is very simple. Notice that here, the problem is that the delta, the good delta, becomes vanishing as x bar goes to plus infinity. So when x can be brought very, very far, up to infinity. At another point of view, the problem here, in the example of the parabola on the positive half line, is that x plus y can grow indefinitely if x and y go to plus infinity. But if we forbid x and y to go to plus infinity, so if we are on a bounded domain, then this problem does not exist. This problem is solved. This is the idea. And this is stated by an important theorem that I will not prove, which is due to Heine and Cantor, that says that f from AB to R, where AB is a finite interval, finite and closed, which is continuous, function is continuous, then f is uniformly continuous. The proof is very beautiful. Sequences, subsequences, and so on, all things that I like. F is uniformly continuous. Namely, for every epsilon larger than 0, there exists a delta that depends only on epsilon and not on x, such that for every couple of x, y in AB, which x minus y less than this delta, we have f of x minus f of y less than epsilon. And this is what we need for the integrability of the continuous function. Okay, this is just a qualitative discussion. I want just to give you the idea of what comes into play in this proof, which sometimes is hidden, underestimated in books, especially in high school books. And this is an advanced theorem in the sense that it is quite technical. You have the means to prove it. If you look for some proof in books or on internet, you have all the tools to understand it. But it is subtle, however. It is much more difficult than the proof of the integrability of continuous function. But you must know that there is this passage to be done, even though we will not face it. Okay? So, and this is the end of this part. Now in next lecture, we will have to complete integrals with the algebra of integrals. There is some elements of algebra also for integrals, and then with the fundamental theorem of integral calculus, which will be the bridge to pass to differential calculus. Okay, have a nice day.